So let's talk about what ends up being a very key concept, set of statements that we're going to kind of build the rest of this course on. Yesterday, I think we finished here. We didn't get to talk about this very much. You guys know what intersections are. If I'm driving down a road and I come to an intersection, it's the place where the roads cross, right? So when I'm in that intersection, okay, I'm in both roads, right? So if we go out here to where Stewart and Bible intersect, and I sit right in the middle of that intersection, I'm actually in both roads, right? Okay. So it's the same thing when we're talking about figures intersecting, and we can have lines intersecting rays, rays intersecting rays, rays intersecting segments, squares intersecting triangles, that kind of stuff. Okay. But whatever points they are sharing is what we call their intersection. Does that make sense? Doesn't have to be 1 point. Could be 2. Could be 3. Now, there are some certain things that, based on the structure of lines, there's only a certain number of ways that lines can intersect. Okay, so those are things that we're going to talk about here in the next couple slides here. Okay, so here is, like I said, one of the most important concepts throughout the entire course. And you're going to start seeing these not only in geometry, these things exist, and they have governed essentially everything you've done in a math class since you first started counting, is attributed to some type of fundamental rule that we basically take for granted, and we assume that it's true regardless of what anybody can show us, okay? So you're going to hear me say these two things, okay? And they're essentially the same, okay? If you ever heard somebody say in like a conversation that a statement is axiomatic, okay? Take this mask off. If they say it's axiomatic, basically what that is saying to you is that it's true, but it can't be proven. But it's just something we're all going to agree on, that it's a true statement, okay? Postulate is another word for that, okay? A postulate is a statement that we have to accept as being true without any proof, okay? There are a lot of statements in this class that you guys know, and I'll explain this to you maybe later on when we have more time. Like, what are you never allowed to divide by? 0. Never allowed to divide by 0. That is a theorem, okay, which means it's something I can actually prove to you why you're not allowed to do that, okay? You've just been told that, right? And you've been told, just accept it, just do what I say, that kind of thing, by a math teacher. And the reason is that probably at the time that you needed to know that, you didn't have enough math to actually prove why you can't do it. But we will prove why division by 0 is something you're not allowed to do, okay? There are some things in math that we can't prove them, but we need to have them to be true, okay? Remember we talked about that undefined set of terms yesterday? If I want to make a definition, I got to have things to start with. I have to have a foundation, right? Postulates are our foundation to show other statements true in this course. We have to have an understanding, this is what we're going to start with, and then we're going to build those things. We're going to say they're true, and then we're going to build those up to create other things, okay? So postulates are true, but we cannot prove them, okay? We can show pictures of them. We can try to manipulate pictures to where it contradicts what is said in the postulate, but at no time will we ever be able to generate a picture that actually contradicts a postulate, okay? So when we start seeing some specific examples of postulates, that might make a little bit more sense. As we go through this, so what I've done is I've cut a lot of our postulates, I've cut them out of a textbook, just cut and paste, put them in my PowerPoints. I do not want you to memorize them by postulate 1-1. Do not memorize them by their name. That should mean nothing to you, because in this textbook it's 1-1, but in another textbook it might be postulate 1-2, or it might be postulate 2-1. Does that make sense? So it's not consistent from author to author, and when you take like standardized tests or whatever, and they ask you for a reason of why something is the way it is, they will never accept, like, hey, that's postulate 1-1 from the Glencoe 2015 textbook. Okay, they want the information that is existing inside here. Okay, so one of the postulates that is something that you have worked on all of last year. One of the key things you guys did last year was you graphed lines, right? And whoever your teacher was, when you graphed lines, how many points did they require you to like have in your T-chart or whatever to graph line? Or whenever you graphed your y-intercept and then you applied your slope to it, how many points did you actually plot before you drew a line through it? 2. And that's because of this postulate right here. Through any 2 points, there is exactly 1 line. Okay? That postulate allows that algebra that we were doing last year to exist. Okay? And think about any 2 locations that you ever highlight in space, so any 2 points, you can always connect them, right? Okay? And you can pass through them in both directions so you can generate a line. Okay? Now, the key thing, so you're going to find out, and then this is a very particular thing, okay, which especially in our everyday language, we don't really we don't concentrate on this very much. We have some leeway with our everyday language that when we get into mathematics can create an issue. So here's where we get a problem. And I highlighted that phrase, exactly 1, because it doesn't say 2. You can't have 2, you can't have 3, you can't have 4. Does that make sense? Okay? If I have A, B up there, no matter how many times I put my ruler through them and draw a line, it gives me the exact same line every single time, right? There's no second, third, or fourth line that creates there, right? Okay? Now, here's where I want to make sure we are all on the same page. On a test or a quiz, what I will do is I will write a postulate out, but I will write it incorrect on purpose. And I'll ask you, is it true or false? Okay? Or is it always, sometimes never true? Something like that. And I could rewrite this and say, through any 2 points, there is a line. Through any 2 points, there is a line. And I'm going to ask you, is that true or false? Okay? And now I'm going to keep that in mind, but I'm going to transfer over to something else that makes maybe a little bit more sense in everyday English. I'm going to tell you that I have a daughter. Okay? I have a daughter. Do you know how many daughters I have total? I have a, but does that mean that I have just 1? Because I have 2. Does that make sense? Okay, so when I use the word a, that is just signifying that I have 1, but I'm not putting a limit on how many I have. But if I say I have 2, now you know how many I have, right? Okay, so when I say exactly 1 line, you know how many I have. If I would just say I have a line, that opens the door to us thinking, could have 2, could have 3, could have 4, right? Okay? So key phrases like that are going to be very, very important. We leave them out in everyday language. We don't think about them like that in everyday language, but in mathematics, they are essential. Okay? So we can't, I know in other classes, like we do vocabulary words or something like that, and you have to like rewrite them in your own words so they make sense to you, right? In math, that's a tricky thing, because when people put things in their own words, a lot of times they leave out phrases like this that could be very damaging if they left them out. Okay? Okay, so our first postulate, we can't prove this. Okay? And basically the reason we can't prove it is because think about the geometry that we know so far. We know about 25 minutes worth of class of geometry so far, and there's nothing prior to this statement that we can kind of stick together that's going to lead us to this. Does that make sense? Okay, so there's no prior information that is bulky enough to add together to create this. So we are going to just make this as an assumption that it's true. We can draw it out as many times as we want, but you're never going to get 2 or 3 or 4 lines to go through A and B. Okay? Postulate, or the second postulate here says, if 2 distinct lines intersect, then they intersect in exactly 1 point. Okay? If 2 distinct lines intersect, then they intersect in exactly 1 point. Okay, so we see that exactly 1. Again, that's key. Okay, if we would just say if 2 distinct lines intersect and they intersect in a point, we're opening that door to say, well, it could be a point 1 singular or 2, 3, 4 could be plural. Okay, so we want the word is exactly 1. What's distinct mean? Different. Okay, think about algebra last year. Were there times last year in algebra when you would graph that sheet, whoever it was that asked you to graph 2 lines and they would overlap 100% on top of one another? Okay, you have infinite solutions. Okay, those were the same line, right? And we had infinite solutions. We had multiple places where they intersected. Okay, when I add this word distinct into this postulate, it eliminates that situation happening. There is no possibility now that we have the same lines overlapping. They have to be different. Okay. The only way, think about this, look at that picture. So that's a scenario, that picture's a scenario of this happening. You got 2 distinct lines, maybe line AE and line BD. They're intersecting and they intersect at point C, 1 exact point. Okay. How could I take those lines? Or think about what you could do to make those lines intersect twice. Okay. So if I wanted those lines to intersect twice, let me just kind of extend some stuff here real quick. So if I extended this line, capital line, keep extending, okay? But now I take this line, and I want it to intersect that other one a second time. I have to do what with it? I have to bend it down, right? What's that violate? Yeah, our undefined term of a line, right? Okay, so because we have those situations, those predefined ideas, and if I want to, get 2 lines to intersect twice, then I need to contradict one of those other facts, okay? And everything we do in mathematics, one fact should never contradict another fact. Does that make sense? Okay. So that ends up being a very, very key postulate for us as we move through the year. All right, so the next one is talking about planes, okay? And I don't like that picture. I don't like pictures about 3-dimensional renderings or images that are done on a 2-dimensional surface. So I'll try to give you a better view of this here in a moment. But it says if 2 distinct planes, okay, so that's different planes, right? Okay, if they intersect, then they intersect in exactly 1 line, okay? In this room, we got planes all over the place, okay? Your ceiling is a plane, right? Does that make sense? Flat surface, extended forever in all directions. It's a plane, or it mimics a plane. This wall here, this wall mimics a plane, okay? Do they ever come in contact with one another? Where at? At the top corner, right? Is that top corner, if we highlighted it, is it a line? Does that make sense? Okay? So anywhere you've got planes intersecting, okay, and they can be of any size, moving in any directions, when they come in contact with one another, they always do so at a line. So let's see here. I've got this somewhere. I think I've embedded this in your Schoology. You can get access to this. But here we've really got 3 planes going on, but that gray one, I don't have anything interactive with that gray one. But you get this red plane and you get that blue plane, right? Now visually, I'm not showing them like expanding forever in all directions, but we can kind of change the size of them a little bit. So that one, so I move that red one around a little bit. Let's take that blue one, slide it up, and we'll slide it that way a little bit. All right, so still not intersecting, right? Okay, but if I take that blue one and now I'm going to slide it along that red one, you see that now there is that intersection, that little corner there that's created, right? Does that make sense to everybody? Okay. No matter how I take those And now I've got those two planes. Those planes they're kind of the same orientation. They're both like kind of like walls, like they'd be that wall there and the wall of smartboards on. But they can be at any angle, okay, to one another. As long as they cross, they're going to always intersect at a line. Is that okay? Okay. When we get to this posture, this one we kind of talked about yesterday. This one I had some people hold hands up in the air, right? And we laid a plane, like a piece of glass on top of them or something like that. Do we do that here? Okay. Says through any three non-collinear points, there is exactly one plane. Okay. Through any three non-collinear points, there is exactly one plane. That's that idea. If we put our hands in the air, no matter where those 3 points are, we can lay a piece of glass or plexiglass or whatever on those three hands. Now, the key phrases here is that right there, that adjective. Okay, the points have to be non-collinear. Okay, if I were to rewrite this as, let's say, I don't want that to be red, but if I should write that, through any 3 points, there is exactly one plane. If that was the phrase, and I put that on a test or a quiz, I asked you true or false, that would be false. Okay? And I'm going to show you an image of why that would be false. If we go here, okay, and the 3 points I want you guys to look at are A, B, and C. Okay? Now, A, B, and C, would you guys agree that those are collinear from what we talked about yesterday? They're on the same line, right? Okay? So that would be an image of a plane, right? Okay? But there is also that plane right there. Does that make sense? That's a completely different plane than that one was. Does that make sense? Okay? And I should be able to, I don't want to highlight that, take this and trace it. And as I move this around, it kind of looks like a bunch of like, the color kind of stinks there for you guys. Let's do it this way. It kind of look like a bunch of like pages out of a book or something like that when I do that. Okay. So those are, have you guys ever seen like party decorations that they unfold and they've got like that cross hatching or whatever? Okay. And they unfold into like a lot of times they're bells or whatever. That's kind of what we got going on here. But each one of those little slices or little pages is an individual plane that is passing through these 3 points, A, B, and C. Okay? So when I make those collinear, we get an infinite number of planes that pass through them. Does that make sense? But once I make them non-collinear, it dwindles that infinite number of planes all the way down to only one. Okay? And that's going to be, like I said, that's going to be pivotal as we move forward too. Okay? Is that cool with everybody? That idea? Okay. We'll stop there. Okay. Wow, got a lot of time left.